Ready to get started? So hopefully you can hear me. We get going today. All right. Today we have in the notes I have some information about the Pre-Veterinary Student Association. They wanted me to share some information about their organization, so that they have some contact information here to learn more about it. So if you aspire to a career in medical care, but you like animals better than humans, then this might be for you. And I'm also the faculty advisor for this organization, although that means pretty much nothing, so take that for what it is. And their color scheme's not working so well on the screen, but you'll hopefully be able to see it better in the PDF that I've posted on Blackboard, or will post. All right, so let's get into today's material, which is going to be on Electron Configuration. So hopefully you got a chance to catch the lecture video that I posted on Tuesday. I think in class, Eric, who filled in for me, might have sort of reviewed some things we'd already covered, but this is the important new stuff that we're going to build on today. So what I covered at the very end of the last lecture that I recorded, and is in the notes now posted in Blackboard, is this diagram here. So it's the periodic table, and it shows how it's arranged in orders of the different subshells that you would be filling in an electron configuration. So the advantage of using the periodic table to do this is you don't have to memorize the order, because it's laid out for you numerically in the periodic table. You just go through one element at a time in the order that they're shown. And also it tells you how many electrons go into each subshell. Because the key thing we're going to be doing, and again we're going to see some examples of it today, is when we write out the electron configuration, we're following the Aufbau principle, which says that we're going to completely fill one subshell before we move on to the next one and start adding electrons to it. So in order to do that, we need to make sure we're putting the correct number of electrons into each subshell. And again, the periodic table tells us that, because the number of elements in each block tells you the maximum number of electrons that can go in to that subshell. So all the S subshells that are these left two columns here have two elements. There's two columns, meaning that you can put a maximum of 2 electrons into an S subshell. If we go to the P block, there's 6 elements that form up the P blocks. That means we can put a maximum of 6 electrons into a P subshell. So we're always going to fill one subshell before moving on to the next. And we do that in order of atomic number until we get to the element that we're interested in. Now the last thing we have to cover before we start doing that is another rule called Hunds Rule. So we learned Aufbau principle last time, which is the building up, filling subshells from lowest to highest. There's one more that also comes into play in electron configurations. Now this one is not so important if you're just trying to figure out how many electrons are in each subshell. But what we can also do is, at times, we'll take it a step further and we'll talk about how many electrons are in each individual orbital and whether they're spin up or spin down. And to be able to do that, you need to also understand what's called Hunds Rule. So the Hunds Rule deals with degenerate orbitals, so it really only comes into play in the P block and the D block, where you have degenerate orbitals, meaning orbitals that are at the same energy. And so when we're filling these degenerate orbitals, the way that we're going to do it, they're all at the same energy, so it doesn't matter which one you fill first. But if we're going to put more than one electron in, the way that we do it is we fill each orbital individually first before putting 2 electrons into any given orbital. So we're going to first put 1 electron into each orbital. And the other key is that when we're putting those electrons one electron into each orbital, that electron could be spin up or spin down, but all of them need to be the same for those individually filled orbitals. So first we start by 1 electron per orbital, all with the same spin. When we draw out some diagrams later, this will make more sense what I'm talking about, but that's the way we're going to follow Hunds Rule. So you're going to do that, individually fill each orbital in the subshell before going back and putting a second electron into any individual orbital. And as I said, this doesn't matter in the S block, because the S block you only have 1 orbital to fill. So you're going to just put 1 electron spin up, 1 electron spin down. But if we get to the P block or the D block or the F, which we're not really going to deal with in this class, you have multiple orbitals all at the same energy, and you need to fill them one at a time, all with the same spin, and then you go and start doubling them up. All right, and another way of stating this rule more concisely is you want to maximize the number of unpaired electrons. All right, the Aufbau principle still is sort of higher up in the food chain. You don't want to violate the Aufbau principle to do this, but in a given subshell where you're filling that with electrons, you want to maximize the number of unpaired electrons in that subshell. Unpaired meaning electrons that have all the same spin. So as many electrons as possible that all have the same spin before you start putting electrons of the opposite spin in. So again, it only matters in the degenerate subshells, which for our cases and in the atoms that are on the periodic table that exist on planet Earth, that's just going to be P, D, and F. And you might ask, well, why does this matter? It's kind of complicated from a quantum mechanical standpoint, so you're not going to be held responsible for the full reasons why, but an easy way to explain it, which is at least partially correct, is that by doing this, you're going to minimize electron-electron repulsions. Because you're always going to put one electron into each orbital before trying to put two electrons into the same orbital. Because if two electrons are in the same orbital, on average, they're closer to each other than two electrons that are in different orbitals. And so by putting them in one orbital at a time, you're going to minimize the electron-electron repulsions, put the electrons as far away from each other as possible. Because even though all those orbitals are at the same energy, remember they're oriented differently in space. So putting two electrons into the same orbital forces them into the same region of space, which makes the electron-electron repulsion stronger. But again, that's not so important that you understand why. So that's the last one. So now let's go ahead and do it. Let's populate some orbitals and talk about electron configurations for different elements on the periodic table. So we're going to start not at the very beginning, but we'll start with two pretty simple elements, boron and carbon, both in the p block. So let's look at how to determine the electron configuration. Then once we do, how to figure out which orbitals are filled and how many electrons they have and the relative spin. All right, so to do this, we're going to have to pull out the periodic table, so I'm going to have to flip back and forth a little bit. And you'll get to see my dog from time to time while I do that. All right, so here's our periodic table. I suppose I could also flip back to page 1 of the notes because that has all the subshells laid out, but we're going to need this. Let me zoom in a little bit. There we go. Okay, so we're going to flip back and forth as much as possible. All right, so if we go to boron, let's actually start with this version of the periodic table that has all the subshells laid out, okay? So boron is here, it's number 5, and so what we're going to do is we're going to add electrons into the different subshells we go through until we get to boron number 5. So we start, oh, stop it. All right, so we start with here, this is 1s1, so we start at number 1, which is hydrogen. This is 1s1, 1s2. Remember that the second 1s element is in a weird spot. It's over here on the right, but this is still 1s. So 1s1, 1s2. After 1s, we come to the second row to the 2s block. So that's 2s1, 2s2. And then when we get to boron, which is where we're going to stop, this is the element we're talking about in this question. This is the 2p subshell, and this is the first element, so it's going to be 2p1. So we stop there. All right, so again, what we're going to do is we started with 1s2. There's 2 electrons that go into the 1s. And then we went to 2s. There's 2 electrons that go in there. And then where we ended on boron is the first element of the 2p block, so that's going to be 2p1. So that would be the correct way to write the electron configuration, which again just specifies how many electrons are in each subshell. It doesn't say what spins they are, what orbitals they're in. And so if you're doing questions on the exam that deal with electron configurations, very often they're going to be multiple choice because it's hard to ask you guys to type out electron configurations in Blackboard. So the first thing you should always do is make sure that it has the correct number of electrons. So if we look at this electron configuration, 2 plus 2 plus 1, there's 5 electrons. That matches boron, which has 5 electrons. So sometimes you can at least eliminate possibilities by making sure the right number of electrons are there on a multiple choice question. So that's a little hint for some of the questions you'll see on the upcoming assignments. But now if we want to put the electrons into the individual orbitals, the way that we draw these types of diagrams is we represent each orbital with a box. So the 1s and 2s blocks each just have a single orbital. Remember, the number of orbitals is given by 2l plus 1, so l is 0 for s subshells. That's going to be 1 and 1. And then for the 2p block, where l equals 1, the second quantum number, there's 3 orbitals. That's how many orbitals there are. And again, that also comes from the periodic table because you can put 2 electrons per orbital. So you have 2, 2, and then 6 for those blocks. So when we fill these with electrons, 1s2 means both electrons have to go into the 1s orbital and they have to have opposite spins. So remember that The Pauli exclusion principle says that if we put 2 electrons in the same orbital, they're opposite spin. So that's 1s2, 2s2 is the same. And then that last 2p electron here, 2p1, can go into any of these 3 because they're all at the same energy, and it could be spin up or spin down. Now conventionally the way we write it, just to keep things organized, is we're always going to fill the orbitals left to right, and we're always going to start with spin up. So that would be the most conventional way to represent that 2p electron and put it right there. Now in reality though, it doesn't matter. So that's fine. This is fine. This is fine. Or we can do all the spin down possibilities. There, there, there. So the arrow, the direction of the arrow represents the spin being up or down, if that wasn't obvious. So we can put that 2p electron in any way we want to. All those are equivalent to each other. So in reality, it doesn't matter, but as I said, by convention, we usually do it that way. But again, if you're doing multiple choice questions where we give you these diagrams, keep in mind that that 2p electron can be in any of those 3 orbitals, and it can be spin up or spin down. There's no energetic difference between those. So if we go to carbon then, which is 1 element over from boron, let me see if it'll let me get my, okay, stop this. All right, so if we go to carbon, which is 1 electron over, so here we're going to again start at the beginning, 1s1, 1s2, 2s1, 2s2, and then to get to carbon, we go 2p1, 2p2. It's the second element in the 2p block, so it has 2 electrons in the 2p subshell. So just 1 additional electron. We're still in the 2p block, so that additional electron also goes into the 2p subshell. Okay, so carbon will be just a little bit different, 1s2, 2s2, 2p2. But now when we write the full diagram out here, where we're going to put the electrons into individual orbitals, we need to make sure we also follow Hunds rule. So 1s2 and 2s2 are going to look the same. They're filled completely, and they have to be like that. But now when we go to 2p2, we can start by putting the first electron as we did before, but now to follow Hunds rule, we have to do 2 things. One is the second p electron has to go into one of the 2 empty orbitals. It can't go into the same one, and it has to have the same spin. So if we start with this, the first electron spin up, the second electron, by convention, will be put there. Set a different orbital, same spin. That's following Hunds rule. Okay, so again, this one here demonstrates Hunds rule, which is important for this particular element where you have a partially filled 2p subshell. Now again, there's a lot of equivalent ways of writing this though. The requirements are, again, the 2 electrons have to be in 2 different orbitals and they have to have the same spin. And there's at least, I think, 6 different ways of doing that or something like that. So you can do, yeah, question in the back? So Hunds rule is where when you have a partially filled subshell with degenerate orbitals, meaning you have either 3 or 5 orbitals at the same energy, what you want to do is you want to put 1 electron per orbital first before putting 2 electrons into the same orbital. And the electrons that you put in individually have to have the same spin. So that's defined in the previous slide up here. But the key is that the 2 electrons that we're putting into these 2p orbitals have to be in different orbitals and have the same spin. So this is valid. That's valid as well. The 2 electrons are in 2 different orbitals with the same spin. Or that works. 2 different orbitals, same spin, or all the different spin down possibilities that I just drew. So this would be fine too, where both of them are down, as long as they're the same spin in 2 different orbitals. Doesn't matter whether they're up or down. Again, conventionally we do left to right, spin up first, so that's the most common way that you'll see it written, but there's a number of possibilities that are all equivalent to each other. So that's how we would do it for carbon, 1s2, 2s2, 2p2. All right, so if we move on then to some heavier elements, it gets a little bit unwieldy at times because if you have a lot of electrons, you have a lot of subshells to fill, you have to keep track of all of them. So there is a shorthand method that you will commonly see. So if we do Na, which is sodium, atomic number 11, let's go through the full configuration for that and just see how it works. First, this one's not too bad because it's only number 11. So again, we're going to go to here, we're going to go in numerical order through all the subshells that come before it. So 1s1, 1s2, this is 2s1, 2s2. As we said, after 2s is 2p, 2p1, 2, 3, 4, 5, 6. We've completely filled 2p. And then we come to sodium, which is in the 3s block. Third row of the periodic table, left column is the s block. So this is 3s1, that's the last electron for sodium. Okay, so the full configuration then for sodium, as I said, would be 1s2, 2s2, 2p6 are all filled, and then the last electron goes into 3s1. Now the way that we often write these configurations, especially for heavier elements that have a lot of electrons, is if we see these filled subshells here, 1s2, 2s2, 2p6, when you fill all the way to a p subshell, that represents this column on the periodic table here at the very end. So we come to neon first, which is over here, number 10, and then we jump down to 11 here. So what we can do is we can represent the electrons from the core that represent these last columns here. We can just use the atomic symbol for that. So we're going to represent the core electrons with an atomic symbol. So the first 10 electrons that we put in, this one. The first 10 electrons that we put into sodium here, 1s2, 2s2, 2p6, those correspond to the element neon, which is atomic number 10. So the way that we can write the configuration more simply is we're going to abbreviate these filled subshells with the noble gas that they correspond to. Noble gas is that last column of the periodic table, which we'll come back to later. So we write that in brackets, Ne 3s1. So this here is the nearest noble gas, which is the last column of the periodic table that comes before it. And so we're going to indicate those inner electrons from that noble gas configuration are going to be indicated with brackets. So the way to interpret a configuration that's written like this is that sodium has all of the electrons that neon has plus 3s1. So it's neon and then 3s1. And again, the noble gas, just to reiterate that, is going to be this last column of the periodic table. So anytime you're doing electron configuration, especially if it's beyond the second row here, what you'll often do is you'll find the noble gas that comes right before that in the series, you'll write that in brackets, and then you'll just fill in the subshells that come afterwards until you get to that element. So that's going to be a way you'll often see it. You should be familiar with how to do the full configuration as well. So again, this notation here, you should know how to produce that, but you're going to commonly see it like this, and this is a simpler and more concise way of doing it. So if we go one element over, which is magnesium, and I apologize if I give you whiplash from flipping back and forth so much today. So magnesium is here, number 12. So the shorthand method for its configuration is we find the noble gas that comes before it. The nearest noble gas to magnesium that comes before it is neon, which is number 10. So again, we're going to write neon in brackets, and then we're just going to fill in the electrons that come after that. So after those inner electrons that represented by the neon configuration, we come down here, 3s1, 3s2, so we stop there at Mg magnesium, which is the element that we're considering. All right, so again, the inner electrons can be represented as neon, that's the nearest noble gas, and then after neon, to get to magnesium, we put 2 electrons into the 3s subshell. Now the other concept that then this brings forward, which is particularly relevant or evident when you look at these shorthand configurations, is the concept of what are called valence orbitals or valence electrons. So these are going to be the ones that represent the outer electrons. So if we're talking about main group elements, these are the elements that have their last electrons in s or p subshells. So those are going to be the ones that are in the S and P block of the periodic table. We'll come to transition elements here in a minute. So for those main group elements, if we want to define what the valence electrons are, those are going to be the electrons with the highest principal quantum number, S and or P. All right, and so if we look at these two examples that I gave you here, how many valence electrons do they have? And the reason that valence electrons are important, as we're going to see, is that these are the ones that are involved in chemistry. So when we're making compounds by forming bonds between elements, or when we're forming ions to make ionic compounds and so on, those valence orbitals and those valence electrons are the ones that are going to be involved in that. Those inner electrons, which we call the core electrons, don't typically matter at all when we're talking about chemical reactions, chemical bonds being formed. So we have to define how many valence electrons they have, and the number of valence electrons they have, as we'll learn, is a predictor of some of their chemical properties. So if we look at sodium here, and especially if we focus on the full configuration, the highest principal quantum number n is 3. That's the 3s subshell that has 1 electron in it. There's only 1 electron that has n equals 3. It's that 3s electron. So that means sodium has 1 valence electron. It's always the electrons that are in the outermost s or p or both in the case of p block elements. And then if we go to magnesium, which is 3s2, there's now 2 electrons with n equals 3. All the rest of the electrons have principal quantum number of 1 or 2. So you have 2 valence electrons for magnesium. And as we'll also see, the number of valence electrons can be predicted by which column in the periodic table you're in. So sodium is in the first column of the periodic table. All of the elements in the first column have 1 valence electron. Magnesium is in the second column. All the elements there have 2 valence electrons. So the location on the periodic table easily allows you to predict that as well. So if we go back to the previous ones for carbon and boron, remember the valence electrons are all of the electrons that have the highest principal quantum number. So for boron, we have 1s2, 2s2, 2p1. So the highest n value is 2 there and there, and there's a total of 3 electrons that have n equals 2, 2s2, 2p1. So this one would have 3 valence electrons. So for p block elements in the p block, it's the s and p that are in the outer shell where they have the highest quantum number, n. And then for carbon, we have 2 electrons in 2s, 2 electrons in 2p, so a total of 4 electrons that have the highest n value. So this would have 4 valence electrons. So for p block elements, it's s and p that define the number of valence electrons. For s block element, it's only the s because you don't have any outer p electrons. Okay, so that's how we count valence electrons. It's going to be a concept that comes up a lot, especially in the next chapter of the course. But we'll introduce it now. And then the last category of elements we'll cover are the transition elements. So transition metals, as they're called. These are the ones that lie in the D block of the periodic table. So we're talking about these elements here that are in the middle of the main part of the periodic table. Those are the transition elements. And they're a little bit more complicated, but we do expect you to be able to predict their electron configurations as well. We're not going to deal with, in great detail, the elements down here. They're a lot more complicated for reasons we won't get into. But we should be able to predict configurations for the transition elements. And the only key difference here is to remember that for the transition elements, so this one here starts as the 3D block, this row here. But before we get to 3D, we have to go through 4s as well. So you're going to fill a S subshell with a higher n value, 4s or 5s, before you fill the D block or the D subshell that's part of. So that's really the only noticeable difference between those and the main groups, is that before we get to that D block, you have to fill the NS subshell, whatever row you're in being N, 4, 5, or 6, and that's going to be filled before the corresponding D subshell, which is technically N minus 1D. So again, in the fourth row of the periodic table where the transition elements start, you're going to fill 4s before you start putting electrons into 3D. So you have to, don't forget about those 4s electrons. A lot of people just skip that over and say, oh, we don't have to worry about those. But they're there and they are going to be filled before you put the D electrons in. And then when we're counting the valence electrons for transition metals, we're going to include those S and D electrons in the count. All right, so for transition metals, all NS and those N minus 1 D electrons that we add in last are going to be counted as valence electrons. And again, that's only for the highest value of N. All right, let's do it, and then we also have to, as we'll see in this example, we have to remember that in some cases we fill the 4F before the 5D and that last row of the transition metals. So let's do this example, which is the most complicated of the transition metals. We'll do two more a little bit later, but this is a fairly complicated one because we're all the way in the last row. So it's OS, which is osmium. Let's find it. Okay, so when we find OS, this number is here, number 76. Now for an element this far down in the periodic table, you're definitely going to want to use the shorthand notation with a noble gas. You don't want to try to write out all 76 electrons or you'll go crazy. So before osmium, the nearest noble gas is here, xenon Xe, number 54. So xenon is 54, osmium is 76. That means we still have 22 electrons to add after xenon. So we have to figure out where those go. So we get here to xenon, that's 54. Those are our core electrons. After that, we come down here. This is the 6th row, so it's going to be 6s1, 6s2. After 6s starts the 5d, but we have to remember that there's a break in the periodic table here. So 5d starts here with number 57, which is lanthanum, but the next number 58 is down here in this cutoff here. Okay, so for this one, the way that our periodic table is organized, you would predict that you would go 6s1, 6s2, 5d1, but then you jump down here, which is 4f. And then you go 4f, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 to get to number 71. That's 4f, 14. Then we go up to 72. We're going in numerical order here. We're back in the 5d. And this is 5d2. This is the second one, 3, 4, 5, and then 6 for osmium. So it's 5d1 from number 57, we skip all the 4Fs, go through those, and then we come back and we have 5 more d electrons to get to osmium. So osmium is in the 6th column of the transition metal block, so it's going to be 5d6. So you have to just remember to put those 4F electrons in this last row of transition metals here, or in the last row of the p block as well. You have to remember that we have those filled 4F electrons. Don't forget to put those in, or else you won't have the right number of electrons. So to write all of that out then, what we get is for osmium, again, the nearest noble gas was xenon. After xenon, we came to 6s2, that we filled the 6s block. Then we got to the first 5d element, but then we jumped down to 4f and filled that, if we're going in numerical order. And then we came back up to the 5d block and had to add 5 more to get to osmium number 76. Now, this is not the conventional way to write this, though. We're going to group these all together. So really, you would write this as follows. Xenon, 6s2, 4f, 14, and then we combine the 5d electrons and write it as 5d6. There's a total of 6 of them. So this is the correct configuration for osmium. It's the 6th element in the d block, so it's pretty easy to see that it should have 6 5d electrons, but we have to remember not to forget about the 4f's. Those are there as well. But we're only going to deal with elements that have filled 4f. We're not going to deal with ones that are partially filled, which is more complicated. But for those last row of the periodic table, make sure you don't forget about going through the 4f block before jumping back up to the 5d or the 5p. Okay? And then if we want to count the number of valence electrons in this element, remember for transition metals, it's the outermost s and d. So there's 6s2, 5d6. That's a total of 8 valence electrons. So for transition metals, you have to count S and D as valence. So there'd be 8 for osmium. 2 plus 6. We don't count the F electrons as valence. Those are never going to be valence electrons for the elements that we deal with, transition metals or main group metals. Only for F elements, which we're not going to ask you about because they're more complicated. All right? And then if we write out the full configuration for osmium, again, focusing on the electrons that come after the noble gas core, we have 6s2, so that 6s is going to be filled. 4f14, so the way that we would fill those is 1, 2, 3, 4, 5, 6, 7, one at a time, and then we start pairing them up. 8, 9, 10, 11, 12, 13, 14. They're all filled, so that's the way it's going to be, but that's the order they would get filled in. And then for 5d, we have 6, and we have to remember that we have to follow Hunds Rule to do this. So we're going to add 1 electron to each orbital first before we start pairing them up. So we're going to go 1, 2, 3, 4, 5 individually paired orbitals, but now for the 6th electron that's in that, we have to pair it up with one of those, and conventionally that would just go with the first one. And 2 electrons in the same orbital have to be opposite spin. That's the Pauli exclusion principle that we introduced last time. So this would be the correct way of writing it, but there's also a number of other equivalent possibilities. You just have to make sure that only one of the orbitals has the electrons paired, and then all the rest have the electrons with the same spin. Okay, so this one would have 4 unpaired electrons. These 4 here, in the way that I wrote it, are all unpaired, meaning that they're 4 electrons that have the same spin without an opposite spin electron next to them in the same orbital. Okay? So any questions on electron configurations and how to use the periodic table to do it? Yes?
I think the 8 valence
So 8 valence electrons, when we're talking about the transition metals, which again are those elements that are in that middle part of the periodic table, the valence electrons are the outermost s and d electrons. So you're always going to have at least 2 from the 6s or whatever s orbitals you're filling for that transition metal, plus whatever d electrons that it has. So this one has 6 d electrons plus the 2s, that's a total of 8. So it's going to be both of those together to define the valence electrons for any transition metal. Any other questions? So this is one of those topics that the best way to learn it is to practice it, which you will get the opportunity to do on the homework assignment, which I think even this week's assignment has some electron configuration questions, and it'll continue with the next week's as well. So I think there's still 2 chapter 2 assignments, so you'll get a lot of chances to practice these concepts. Please come to me if you have any problems figuring it out. Now the last thing we'll cover with respect to electron configurations are a couple of cases where there's exceptions to what you would predict. So you might ask yourself, well, if I use the periodic table to predict the electron configuration, again, going in order of the different subshells, filling the lower energy subshells, then the higher energy subshells, does that work 100% of the time? And the unfortunate answer is no, it doesn't work 100% of the time. And that's particularly true as we get down to, as we get down to this part of the periodic table here, because a lot of these subshells, you know, the 6s, the 4f, the 5d, like we just talked about, those are all really close in energy to each other. So sometimes it's hard to predict what order they fill in. There's no really rational way to do that. But we're not going to hold you responsible for all the many exceptions that there are. There's just 2 that we want you to be aware of. So 2 cases where the electron configuration that you would predict do not actually match what's really happening. And those are going to be 2 transition metals, chromium and copper. So if we predict the electron configuration for chromium, let's do that first. So we can use the periodic table to predict, but as I said, in this case, it's not quite right. So for chromium, which is Cr right here, the nearest noble gas is argon, so we'll write that as our core. And then after argon, we go to the 4s block. So it's going to be 4s1, 4s2, and then 3d, 1, 2, 3, 4 takes us to chromium there. Okay, so we go through the 4s first, then the 3d. Chromium is the 4th element, so we would predict that it's a 3d4 configuration. So that's what we would predict. All right, so let's write that out. So if we just blindly use the periodic table, this is what we get. But it turns out that this is not quite correct in the actual configuration. So let me cross that out so you don't think that is correct. The actual configuration is what we're going to do here. We're not changing the number of electrons. It still has the total, 24 electrons that chromium has. But we're going to take one of the electrons from 4s and move it up to 3d. 4s and 3d are pretty close to each other in energy. They're not that different from each other. So it's not a big deal to move one electron from 4s to 3d. So what we write instead, which is the correct configuration, is 4s1, 3d5. Still 6 valence electrons, but we've taken one of them from the 4s and moved it up to the 3d. Now the reasons for this are fairly complicated quantum mechanically, so we're not going to cover them here. The way that you sort of remember it, even though it's not a very satisfying explanation, is that half-filled subshells are often more favorable. All right, and that doesn't get into the reasons why that's true at all, and the reasons why are quantum mechanical in nature, so I'm not going to attempt to cover them in a general chemistry course. But here, instead of having a filled 4s and a partially filled 3d, we have a half-filled 4s and a half-filled 3d. Because remember that the 4s subshell can hold 2 electrons, so now 4s1 is half-filled. The 3d subshell can hold 10 electrons, so 3d5 would also be half-filled. So making those half-filled subshells can be favorable in some cases, so this is one we expect you to remember. As I said, only 2 that we expect you to remember, so don't get too worried about this. And then for copper, we have a similar situation occurring. So if we predict the electron configuration for copper, if we go back to the periodic table, copper is here, so it's still going to be argon for the core electrons, 4s2, and then 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. Copper is the 9th element in the 3d, so we would predict that it ends with 3d9. All right, so this is what we predict for copper. By just looking at its location on the periodic table and filling in the electrons one at a time. But again, that's not quite correct, and we're going to do a similar thing here. We're going to take one electron from 4s and bump it up into 3d. So the actual configuration for copper is 4s1, 3d10, where in this case, we're able to fill the D shell completely, go from 3d9 to 3d10, which is now completely filled. So without getting into the quantum mechanical reasons for that, this filled D subshell ends up being favored, so it's net favorable to promote one electron to that orbital. Because these are still the ground state configurations, the lowest energy configuration, but these two configurations do not perfectly follow the off-bow principle because they don't completely fill the 4s subshell before putting electrons into 3d. Those are the only two exceptions we expect you to know. There are many more than that in the periodic table, especially as you go down further and further into the lower rows. But for any other one, we would just ask you to predict the electron configuration from the periodic table, and that would be the answer that we'd be looking for in that, even though there are a lot of exceptions. But these two, we want you to know, they differ a little bit from what you would predict. All right, so that takes me to the end of electron configurations. Any last questions on that? Yeah, in the back, one. So how we determine what? The variance. Valence electrons? No, so that actually doesn't change because it's still the sum of S and D. So whether you write it in the predicted way or the actual way, it's still 6 for this one. Sorry, I skipped that. 2 plus 4 is 6, or 1 plus 5 is still 6. So the number of valence electrons doesn't change by virtue of having these slight differences in configuration because it's still defined the same way as S plus D for a transition element. So yeah, you're not typically going to change the number of valence electrons, you're just going to change the way they're arranged in the different orbitals. And then another question back there? So the question about electron configurations, if you couldn't hear, and especially for people on YouTube, was whether we can do it for anions or only for neutral elements. And the answer is yes, we can do it for anions and cations, and we're going to get there in a little bit. So you always start with a neutral element, but then for anions and cations, you take out or remove electrons, or add or remove electrons to the highest subshell. So anyway, you can do it for anions and cations. It's typically a little bit very similar, a little bit different in some cases, so we'll get to that in a little bit, but that's a good question. So that's coming. All right, now the reason that electron configurations are important and the whole organization of the periodic table is important is that it defines, as I said, a lot of the chemical properties of the elements based on where they're located in the periodic table. And so what we can do then is we can define different columns or different sections of the periodic table where we sort of categorize the elements in different ways, and that's going to then dictate in a broad sense what their properties are. So the periodic table, the grossest division is to divide the left from the right of the periodic table. So there's this imaginary staircase that it starts at boron and goes down like this, where anything on the left is going to be metals. So the most basic division of the periodic table is metals to the left, and then because we couldn't come up with a more creative name, nonmetals to the right. So this imaginary staircase, it's not shown on the periodic table that you have for your exams, but it starts at boron and just snakes down to the bottom. Anything to the left of that is typically classified as a metal. Anything to the right is a nonmetal. That's kind of the most coarse division of the periodic table that we have. And as we'll learn, nonmetals and metals have very different chemical and physical properties, which we're going to come to a bit later in the course. But within each of those parts of the periodic tables, there's going to be more specific definitions given as well. So first, let's just highlight all of the nonmetal elements and just do that in blue. So we're going to highlight nonmetals in blue. Let me do different colors for all of these. All right, so the nonmetals are going to be highlighted in blue, and that's going to include the whole noble gas column. It's going to include this whole column here, and then again up to the staircase. So there's a few elements right along the staircase that are going to be classified a little bit differently, so we're going to talk about those in a little bit. But those are going to be your nonmetal elements there that are shown in blue. All right. And then within the metals on the left side of the periodic table, we have a few different categories we want you to know. So the metals that are in the S and P block are called main group metals. So we're going to put those in green. So there's two major categorizations of metals. Main group metals, which means they occur in the S block or the P block, or the transition metals, which are the ones that we talked about are in the middle. So the main group metals, which I'll highlight in green now, is going to include these entire first row of the periodic table except for hydrogen. I forgot to put a blue highlight on hydrogen. Hydrogen, even though it's on the left side of the periodic table, is a nonmetal, so don't be confused by that. It's, again, just the way the periodic table is arranged, doesn't quite work for hydrogen. So hydrogen is not a metal, but it's the only non-metal on the left side. But the rest of these two columns are called main group metals. And then also below the staircase, or to the left of the staircase in the P block, would also be some main group metals. So the whole rest of this column here below the staircase, and then I want to make sure I get these right. So tin and lead, bismuth, polonium. I'm doing the wrong color, crap. So those should be green. Those are all main group metals, okay? So that's going to be, again, to the left of the staircase in the P block of the periodic table. All right, so those are going to be our main group metals, and green there. And then in the middle here, we're going to put, as we kind of already known, the transition metals. Which will be highlighted in pink. So the transition metals are going to be the ones that, again, they're these middle 10 columns of the periodic table there. And I guess technically these ones, but these are all man-made, so we don't really have to worry about them too much. But this is a slightly bigger periodic table than you guys have. It includes some of the more recent discovered elements, but all those ones in the middle are the transition metals. And then finally, the last category of metals we have, I guess there's technically three categories. I gotta make sure I find a unique color for this. That's gonna be these ones down here, which are gonna be those F blocks. So these are the F block elements, and what we call those in terms of their name is going to be inner transition metals. So that's shown in orange. Inner transition metals. So remember they're cut out here from the transition metal series in the right there and there as it's shown here. So those are the inner transition metals, which are shown at the bottom of the periodic table, but in reality are cut out from these two rows there and there. And then finally, the last ones that I have not highlighted yet are going to be, and do I have another color left or not? Let's see, which color have I not used? I think I haven't used red yet. Okay, so we'll do red for the last ones. I hope if you're colorblind, this diagram is not going to make a lot of sense, but there are better ways of showing it. All right, so the last ones which I have not yet highlighted are some of these elements that are right along the staircase here. And those ones, depending on what textbook you look at, you might see different elements classified in this way. So all the elements along the staircase, like it's sometimes a little bit debatable. Are they metals, are they non-metals, or are they this third category? But the ones that we conventionally define in this third category are called metalloids. And they're going to be shown, again, these ones right along the staircase: boron, silicon, germanium, arsenic, antimony, and tellurium. Okay, so again, you might sometimes, some sources might categorize other ones that are close to the staircase as metalloids. Like sometimes I think I've seen bismuth or tin categorized as a metalloid, but tin's more of a metal. But these six here, boron, silicon, germanium, arsenic, antimony, tellurium, which are all right along that staircase, they're called metalloids. And what that really means is that their properties are in between a non-metal and a metal. So they're not cleanly categorized as either of those. They have some properties that make them kind of like a metal, but they have other properties that make them kind of like a non-metal, so they're kind of the in-between elements because they are right on the borderline between metals and non-metals. So you should be familiar with most of those as well as being metalloids, especially boron, silicon, germanium, arsenic. Those are your four most common metalloids, and we'll, again, at the very end of the course, we'll talk about some of the properties that arise from that. All right, so that is kind of how we sort of categorize the different elements on the periodic table. There's a couple of subcategories that we should be familiar with as well. So within the main group metals, we have two different columns here. So this first column here is called the alkali metals. So that's one type of main group metal that we have. Is called alkali. That's the first column, and that's everything except for hydrogen that's in the first column. Hydrogen is a non-metal, as we said, but lithium, sodium, potassium, rubidium, cesium, francium, those are all of our alkali metals. And then this second column here is called the alkaline earth metals, so it's not too different in name, but it's a different category. So that would be beryllium, magnesium, calcium, strontium, barium, and radium. So those are your different categories of main group metals that we want you to know. And then we also have, so the first two columns have their own sort of categories associated with them. We want you to know those. And we also want you to know what the last two columns are called as well. As we've already referred to today, this last column of the periodic table is called noble gases. And noble not in the sense that they hold a high title or own a lot of land, but that they're unreactive. It's another way of saying that they don't really do a lot of chemistry. They're sort of inert is another way of saying that. So that's helium, neon, argon, krypton, xenon, and radon. So those are your noble gases. And then the second to last column here is called the halogens. So we want you to be familiar with that term as well. All right, so fluorine, chlorine, bromine, iodine, and acetylene, those are your halogen elements. Okay, so those are the categories we want you to know. And metals versus nonmetals, main group metals versus transition metals being one sort of subcategory, the metalloids, which are the borderline ones, and then a few different categories. So there's kind of a lot of information on this, but again, the more you use this terminology and the more you see it, it should become familiar and kind of second nature. There's, the way I like to look at it is you can't learn a language if you don't know the vocabulary. So we're learning the language of chemistry, and this is some of the important vocabulary associated with that. This is how we classify elements, and how that's going to then determine their chemical and physical properties, which we'll cover throughout the course. All right, so that's going to be how we can also use the periodic table to predict certain categories of elements. Now what we're going to do for the second half of today's course is talk about how we can use the periodic table to predict certain properties of elements, at least in a relative sense. So we're going to compare properties of elements to each other, and we're going to talk about three of them mainly, and how we can look at where that element is in the periodic table and decide whether that is going to increase or decrease relative to another element on the periodic table based on their respective locations. So the first property we're going to talk about is atomic radius. An atomic radius is essentially the size of the atom. So the distance from the nucleus to the sort of outer edge of the electron cloud, however that's defined, that's going to define the atomic radius. It's how much space the electrons take up around that atom. And the way that it's measured is different depending on the type of element you're talking about. So for metals, as we'll learn at the very end of the course, metals tend to have regular arrangements of the atoms. They all kind of line up in these regular rows. So if these are all the atoms in a metal, they're kind of all clustered close together like this. And we have a lot of different techniques available to us for measuring the distance between two nuclei in a metal. So all these little dots here represent the nuclei for the metal. And if we measure this distance here, that distance, half of that distance is going to be what's called the atomic radius. So we call that more specifically the metallic radius if it's a metal, but more generally it can be called the atomic radius, and it's going to be equal to 1/2 the distance between adjacent nuclei. All right, so we don't have a good way of looking at an individual atom and measuring, how much space the electrons take up and defining the radius like that directly. But if we can measure the distance between two nuclei in a metal, and then we would say that the radius is half of that distance. Because as we go between two, we're going to go to the outer edge of this atom, and then from the outer edge of the second atom to that one, so half of that will be the radius of one atom. So that's how we sort of measure it or define it, but again, what it really means is just the size of the atom. And then for nonmetals, the way it's done is, for some nonmetal elements, they exist in diatomic form. So for example, chlorine exists as Cl2, so these are now discrete molecules of chlorine. And we can likewise use different techniques to measure this distance here between the two nuclei, which for chlorine comes out to 199 picometers, where picometer is 10 to the minus 12 meters. So again, a very small distance for atoms, they're tiny. And then what we would define as the radius of a single chlorine atom would be again, that number divided by 2. So it's defined in a similar way. It's just we're talking about for nonmetals molecules instead of bulk metals like we have for the other half of the periodic table. So we can get a radius for chlorine that's 100 picometers. Now, not all elements, though, not all non-metal elements exist nicely in those sort of diatomic forms that we can easily measure the distance between. So the other way we do it is we can take two different elements bonded together, like carbon and chlorine. So if that's a carbon and that's a chlorine and they're bonded together, we can measure the distance between those two nuclei, which comes out to 177 picometers, so we're putting real numbers on it. And this distance would represent the sum of the atomic radii for chlorine and carbon. So we know chlorine from the measurement we did on chlorine itself, so then we can do a little bit of algebra and find that the radius for carbon comes out to 77 picometers. So it's 100 for chlorine, 77 for carbon. That places the distance between the two nuclei at the sum of those, which is 77. So that's just a little bit of background of how we determine those. So in reality, when you see numbers quoted for atomic radii, they're kind of like average numbers over a whole bunch of different compounds. So they're going to measure a bunch of different compounds that have different combinations of elements bonded to each other, and those averages are what are typically reported as the atomic radius. So it's sort of an approximate number. It's not exactly the case because we can't directly measure the size of an atom. There's no good technique for doing that, but we can measure the distance between nuclei, and that's then related to the size of the atoms. But it can vary a little bit from compound to compound, so you're not going to get the exact same number every time. But what we want to know in this class are the trends for atomic radius. So how do we predict whether the radius is going to be bigger or smaller when we're comparing two elements or more than two elements to each other? And that's what we're really going to deal with in this course, okay? So here's the general trend for atomic radius. It comes from the periodic table. So let's just think about it a little bit. What do we think happens? So in the periodic table, a group is a column and a period is a row. But let's just use column and row for now. So if we go down a column in the periodic table, which we call a group of the periodic table, let's think about what happens. So remember that the way the periodic table is organized is as we go from top to bottom, each row of the periodic table represents a different principal quantum number n for that block of the periodic table. So n equals 1, 2, 3, 4, 5, 6, and so on as we start that row of the periodic table. So as we go down the periodic table, the principal quantum number n is increasing. Again, as we go from top to bottom. And as we talked about all the way back with the Bohr model, and then continuing on with this part of the course, the principal quantum number n, one of the things that it determines is, on average, how far the electrons are from the nucleus. So even back with the Bohr model, which assumed circular orbits, we saw that n equals 1 was close to the nucleus, n equals 2 was further, n equals 3 was further than that, and so on. So as the principal quantum number of the outer electrons increases, on average, they get further and further away from the nucleus. So because the electrons are getting further away from the nucleus as we go down a column, that means that the atoms, the size of the atom is going to increase as we go down that column. So as we go down a column of the periodic table, the atoms get larger and larger and larger as we go from top to bottom. So that's the first part of the trend. Now as we go across a row of the periodic table, or what is more precisely called a period, so a horizontal row of the periodic table is called a period. This one's a little bit harder to think about, but basically as we go left to right, we're putting electrons, the outer electrons, into similar subshells. I mean, at least the same principal quantum number, or at least similar to that in terms of their distance from the nucleus. But as we go left to right, we're adding more and more protons to the nucleus while keeping the number of core electrons the same. So remember that term we talked about, Z effective, the effective nuclear charge that's felt by the outer electrons? As we go left to right, the Z effective increases. We're adding more protons to the nucleus as we go left to right because the atomic number is increasing. And what that's going to do is those outer electrons are going to get pulled closer in. Because if you have more protons in the nucleus, there's a stronger attraction to the outer electrons, and that pulls them a little bit closer. So Z effective increases as we go left to right. That means the electrons are going to be pulled closer, and that would then cause the radius to decrease. Here we're going left to right just to make sure you're clear on that. Electrons, and then that means the radius decreases. So if we want to write out the trend for increasing atomic radius, which direction do we go on the periodic table to see an increase in atomic radius? It's going to increase as we go top to bottom, and it's also going to increase as we go right to left. Okay? Yes? So again, we'll come to cations and anions later and talk about their atomic or ionic radius, as it's called in that case. So the principal quantum number still matters for those, but you also have to think about whether you're adding or subtracting electrons from the outer shell to form an anion or cation, which will then affect the radius. So to give a short answer for what we're going to talk about later, for a cation, when you remove electrons, the radius shrinks a lot. For an anion, when you add electrons, the radius gets bigger relative to the neutral atom. So that's the important concept there, but we're going to again talk about that in more detail later. But this trends that we're giving for now only deal with neutral atoms on the periodic table. So the atomic radius will increase as you go down a column or as you move right to left across a row of the periodic table. All right. Now the next property we're going to talk about is called ionization energy. We introduced this a little bit in the context of the Bohr model, where we saw that the Bohr model allowed us to calculate the ionization energy for hydrogen. But what the ionization energy refers to is the energy required to remove one electron from a gas phase atom. And when we're removing that one electron, so you remember that the outer electrons are the ones that are attracted most weakly to the nucleus because they're the furthest away. So that electron that you remove is going to be one of those outer electrons. So it's going to again be dictated by where the valence electrons are in that atom. So the net sort of reaction, if you want to think about it that way, is ionization energy. We have an atom that's a gas, and we remove one electron to make a positive ion, which is also still in the gas phase, and release a free electron. And the change in energy for this process, how much energy has to go in for this to happen, is equal to the ionization energy, which we'll abbreviate as IE1 because it's removing the first electron in this case, and that's going to be always a positive number bigger than 0. So it takes energy to remove an electron from an atom. You have to break that attraction. So the factors that influence it are kind of related to what we just talked about with the radius. So as we go down a group, again, the group being a column, top to bottom, the principal quantum number increases and the radius increases. So as your radius increases, the electron gets further away from the nucleus, and that makes the attraction of the nucleus weaker. So as you go and increase the radius, the ionization energy becomes smaller because it's easier to remove the electron. So if the electron is attracted to the nucleus more weakly, the ionization energy will decrease. And then similarly, as we move across a period, for the same arguments we use for radius, as we move left to right, we're increasing the effective nuclear charge, adding protons to the nucleus. And that causes the size to decrease. So as we move left to right, the atoms get smaller. The electrons are then held more tightly because they're closer to the nucleus, and that makes it harder to pull them off, meaning the ionization energy increases. So in that case, the attraction to the nucleus increases, which means the ionization energy decreases. So those are the trends for ionization energy. In some sense, they're opposite of the trends for radius. So if we want to draw the trend for increasing ionization energy, it's going to increase as we go bottom to top as the atoms get smaller and the electrons get closer to the nucleus. It takes more energy to pull them off. And it's going to increase left to right as we add more protons to the nucleus. And again, the electrons are held more strongly. So that's the trend for ionization energy. So it tends to be highest as you go to the top right corner of the periodic table. Now there are some blips in the trend which occur at group 2 and group 5. So that's going to be here, the second column, and here, the middle part of the P block. So there's some blips in the trend there. So as we go across the groups in the periodic table, And this is ionization energy. And we're only going to be considering the main group elements for this. We're not going to worry too much about transition metals. So when we talk about group 1, 2, 3, 4, 5, 6, 7, 8, that's going to be these main group columns. So 1, 2, 3, 4, 5, 6, 7, 8. Those 8 columns of the periodic table. So as we go across left to right, again, the general trend is that it increases. So you'll see sort of a general increasing trend left to right. But if we look at the specific values in each of those columns, what you'll find is that group 2 and group 5 have abnormally high ionization energies. Because the filled S subshell that you have in group 2, S2, and the half-filled P subshell that you have in group 5, which is P3, those are particularly stable and they don't want to lose an electron. They want to hold on to that electron more tightly. So group 1 would be somewhere here, low ionization energy. Group 2 is abnormally high, so you'll see a decrease as you go from 2 to 3, but then it'll increase 4, and then again, number 5 here is going to be abnormally high and off the trend as well. And then it's really high for noble gases, but they're all the way to the right and they're the highest still, so you don't have to really remember a break in the trend there. But there's 2 breaks in the trend which occur at group 2 and group 5. So as you go from 2 to 3, the ionization energy tends to decrease from this column to that column, and similarly as you go from 5 to 6, the ionization energy tends to decrease as you go from this column to that column there. Okay, so there's some breaks in the trend that you have to be familiar with, some exceptions to it's not a steady increase from left to right, but group 2 and group 5 are abnormally high and they lie off of that trend a little bit. Okay, so that's what you should know for ionization energy and how to predict them relative to each other. And then for the last thing we'll talk about with ionization energies is successive ionization energies. So we said that the first ionization energy is defined as removing the first electron. So you have a neutral gas phase atom and you remove an electron to form a cation and release 1 electron. But then we can also define additional ionization energies which refer to the energy required to remove additional electrons, the second electron, the third electron, and so on. So the second ionization energy would be where we start with the cation, where we've already removed 1 electron, and we take off a second electron to make the 2+ cation. So again, we can define ionization energy successively for the removal of each additional electron from the atom to form higher and higher charged cations, 1+, 2+, 3+, and so on. So for any element on the periodic table, the ionization energy is going to increase as you do that, because when you form the cation, you have now fewer electrons, so they're able to be attracted more strongly to the nucleus and less electron-electron repulsion. So it becomes harder and harder to remove the electrons as you increase the charge. So what that means is that for a given element, the first ionization energy is the smallest, and they're going to increase as you go higher and higher. So, and that's what we're showing here. We have nitrogen and oxygen listed here. We see that for both of these, the ionization energies increase as we remove more and more electrons. Each number is bigger than the one before it. All right, that's because just in general, it's harder to remove an electron from a cation. Okay, because those higher order ionization energies require you to remove an electron from something that's already positively charged, and that's harder to do. All right. And then what we also will see is that we're going to see a huge jump, though, once we've removed all the valence electrons. So even though it's going to always increase, the increase is going to be pretty steady as you're removing valence electrons. But then once you've removed all the valence electrons, removing a core electron, which is much closer to the nucleus, requires a lot more energy. All right, and that's because, again, they're closer to the nucleus, so it's hard to remove those core electrons. So if we look at the nitrogen and oxygen examples up here, the valence configuration for nitrogen is 2s2, 2p3. It's in the third column of the p block, so it has 5 valence electrons. And then for oxygen, it's 2s2, 2p4. So what we see with nitrogen is that if we go through the different ionization energies, they're steadily increasing, steadily increasing, steadily increasing. But after IE5, where we've now removed all of the valence electrons, the sixth one, which will require us to move a core electron, gets much higher. So it's going, 1.4, 2.8, 4.6, 7.5, 9.4, all the way up to 53. So there's a huge jump where all of a sudden the ionization energy gets much larger, and that's because for the sixth one, we're starting to remove core electrons beyond these 5 valence electrons. But then for oxygen, which has 6 valence electrons, we see that we have a steady increase until ionization energy 6, and it's not until the 7th one that we see the huge jump in ionization. All right, so the trend in ionization energy is where you see that big jump can tell you how many valence electrons the atom has. So again, for nitrogen, it occurs after the 5th, which means that you have 5 valence electrons. For oxygen, the big jump, 13 to 71, doesn't occur until after the 6th because you have 6 valence electrons. So that's another concept related to successive ionization energies we want you to know. All right, we're going to keep moving because I'm a little behind, but we should be able to finish just about everything today. The last concept we want to talk about periodic trends for is electron affinity. And in some sense, electron affinity it's not really the opposite, but it's kind of can be thought of as the opposite of ionization energy. So it's going to be the energy change associated with adding an electron to an atom. In other words, for forming an anion. Now it's a little bit more complicated because it can be negative or positive. It's usually negative because you're forming a new attraction between the proton in the nucleus and the electron that you're adding. But it's how much energy is changed when you add one electron. Oh, I'm not writing correctly here. Energy change accompanying the addition of one electron. All right, so the sort of transformation looks like this. You're starting with a neutral atom in the gas phase, and this time you're going to be adding an electron to it to form a negatively charged ion. All right, and the change in energy for this process is called the first electron affinity, if it's the first electron that you're adding, and this is usually a negative number, meaning that the energy decreases as you add the first electron. Beyond the first electron, it's not usually favorable, but for the first electron affinity, it's usually a negative number. So when we say that something has a higher electron affinity, we mean that it has a more negative electron affinity. The magnitude of that number is what we're talking about with electron affinity. So how big in magnitude this number is how we would define the size of the electron affinity. So the factors that influence it are sort of the same as what influences the ionization energy. The size of the atom. Larger atoms have smaller electron affinity because the electrons that you'd be putting in are further away, so they have a smaller attraction to the nucleus, so that releases less energy when you add them. All right, so you typically have smaller or less negative electron affinity for larger atoms, and also then that same effective nuclear charge. Now we'll see there's some exceptions to this, but in general, if you have a higher nuclear charge, again, which is what occurs as we move left to right on the periodic table, that leads to a larger, or what we say is more negative, electron affinity. So an electron affinity can be thought of as how badly the atom wants an additional electron. If the atom is small and the electron can get really close to the nucleus, then it wants that electron more badly because it can form a stronger attraction. We're always trying to form strong attractions between protons and neutrons. If you have more protons, again, it wants another electron more badly because it has more protons to attract to that electron, and you form a stronger interaction. All right, so that's what electron affinity is, and the general trend is the same as ionization energy. It tends to increase as we go bottom to top and left to right. So basically the same trend as ionization. So that's what I'm showing here is the increasing, or again, more negative electron affinity. But this trend is likewise not very smooth. So if we again draw out the plot here, this is going to be the absolute value of electron affinity, because again, electron affinity is typically a negative number. So the larger this number is, the more what we say is a higher electron affinity. We're going to go across the different main group elements: 1, 2, 3, 4, 5, 6, 7, 8. All right, and again, that tends to increase. It's an increasing trend as we go left to right. So that basic trend is still followed, but we have the same sort of breaks in the trend that we have for ionization energy. So the group 2 elements And that's where you have an S2 configuration. Remember that this S2 configuration here is somewhat stable. So those elements don't want to lose an electron. That means they have a high ionization energy, but they also don't want to gain any more electrons because they want to stay at that S2 configuration. So they have an abnormally low electron affinity. And then similarly for group 5, which is that P3 electron configuration, those likewise have low electron affinity because they're happy as P3. That's a relatively stable configuration. So they don't want to lose electrons, which is why they have a high ionization energy, and they also don't want to gain electrons, which is why they have a low electron affinity. So you just have to remember that those breaks in the trend occur in the same spot for both ionization energy and electron affinity, both at group 2 and group 5, but it's opposites. So group 2 and group 5 have high ionization energy and they have low electron affinity. They don't want to change the number of electrons that they have. Okay, so what that would look like then is that you have sort of abnormally low electron affinity for group 2, abnormally low for group 5. They tend to be actually like positive numbers. And then you go up to group 6 and group 7. And then for group 8, they have like basically no electron affinity because they're noble gases. So the most stable configuration is the noble gas configuration, which is this column here. And in that case, they definitely don't want to add or remove electrons. So they have very high ionization energies, but that doesn't really break the trend. But we don't even really talk about the electron affinity for noble gas. They basically have no electron affinity. They want to stay with the exact same number of electrons that they already have. Okay, so it's again group 2 and group 5, where this time though they have abnormally low values because they don't want to add electrons. So those are the 3 trends that we'll cover. And then what we'll get into with the very last little bit of time we have today is the formation of ions. So this was a question that already came up a couple times, and now we're going to start getting into it. And I think we're technically on to chapter 3 now, if you want to keep track of where we are in the book. I think chapter 3 starts with ions. So we finished chapter 2, which ends with those periodic trends. Now let's talk about the formation of ions and predicting which ones are going to form, which we can easily do for the main group elements. Again, for transition elements, it's more complicated, so we're not going to hold you guys too responsible for that. But for the main group elements, the metals, which are the first 2 blocks of the periodic table, or the non-metals, which are on the right, we can predict whether they're going to form positively or negatively charged ions, and we can predict what that charge is going to be based on the location on the periodic table. All right, so the main group elements are going to lose or gain electrons until they get the same number of electrons as the nearest noble gas. So as we said, the noble gas configuration is the most stable configuration you can have. And so when you're forming an ion, the element is either going to lose electrons until it gets to the noble gas, or it's going to gain electrons until it gets to the noble gas configuration. That'll allow you to predict how many electrons it will lose or gain. And so there's a very simple trend as we go through the different groups on the periodic table. So group 1A, that's the first column of the periodic table, which is that the alkali metals. Those have a valence configuration of S1, and if they lose 1 electron, they will then acquire the configuration of the noble gas. So going back to the periodic table quickly, this whole first column of the periodic table, if they lose 1 electron, lithium loses 1 electron, it becomes the configuration of helium. Sodium loses 1 electron, it would get the configuration of neon. So by losing 1 electron, all of these elements in the first column can get to the noble gas configuration that comes before it. So all of those would tend to form +1 cations. So the whole first column of the periodic table, you would predict that the stable ion that they would form is a +1 cation. And that's going to be true for all the elements in that column: lithium, sodium, potassium, rubidium, cesium. I think there might be one other one, but those are the main ones that we'll talk about. If we go to group 2, by the similar argument, this has a valence configuration of S2. It just has 2 additional electrons beyond the noble gas. So now if it loses 2 electrons, it will also achieve the noble gas configuration. By losing 2 electrons, it would tend to form a +2 cation. So beryllium, magnesium, calcium, strontium, and barium all lose 2 electrons. That gets them noble gas configuration and leads them to them forming a +2 cation. If we go to the non-metal side of the periodic table, group 5, group 6, and group 7, so that's going to be these columns here, 5A, 6A, and 7A, being the nitrogen, oxygen, and fluorine columns. Those ones, it's easier for them to gain electrons to get to noble gas configuration. So they're closer to the noble gas by gaining electrons instead of losing electrons. So the nonmetals tend to gain electrons and form anions. So in the fifth column here, group 5, if you gain 3 electrons, 1, 2, 3, that takes you to the noble gas configuration. In the sixth column that starts with oxygen, you can gain 2 electrons and get to the noble gas, add 2 electrons, and then for fluorine it just needs 1 electron to get to the noble gas configuration. So for the nonmetals on the right side of the periodic table, they will gain electrons because they have an S2, in this case P3 configuration for group 5. It wants to get to S2P6, which is the noble gas, so it has to gain 3 electrons in that case. So you would predict that this forms -3. And the 2 elements that do that are nitrogen and phosphorus, which form N3- and P3-. Below that, they tend to have more metal character, so their ions are less predictable in that case. But for those first 2 elements in group 5, you see that. Most of group 6, you see that as well. So they would gain 2 electrons because they're S2P4. So with 2 additional electrons, they can get to S2P6, which is where they want to be. So oxygen would do that, sulfur and selenium. Again, below that, you get close to that staircase, so they start to behave more like metals, and it's harder to predict. But for those 3, and then for all of group 7A, which have S2P5 configurations, they can gain a single electron, form a -1 anion, and get to the nearest noble gas. So you see that for all the halogens, at least all the non-radioactive halogens that we'll talk about, which are these 4 here. Fluorine, bromine, chlorine, bromine, iodine, all gain 1 electron to form -1 anions. So that's how you predict which anions and cations would form. And then from there, we can start to talk about their electron configuration, which was another question that came up earlier. How do we predict that? So we always start with the neutral atom, and then we're just going to, for anions, it's pretty simple. We're just going to add electrons to the partially filled p subshell. Because as we said, these anions, they want to achieve noble gas configuration. And so in the nonmetals that do this, you add electrons to their partially filled p subshell until the p subshell is completely filled and you get to the noble gas configuration. So if we have oxygen as a neutral element, oxygen has a configuration of 1s2, 2s2, 2p4. I don't think we talked about that one earlier, but it's in the 4th column of the p block, so that's its configuration. We already said in the last slide that it wants to gain 2 electrons and get to the noble gas. And so it does so, and we add those 2 electrons to the partially filled p subshell. So we just add the electrons to whatever available subshell we have, just like we would for the Aufbau principle. So for 2p4, it's not completely filled, so those 2 electrons can still go into the 2p, and you'll get to O2-, which has a 1s2, 2s2, 2p6 configuration. We've added 2 electrons to 2p, and that equals the configuration of neon, which is a noble gas. So again, those anions and cations tend to form noble gas configurations. And then for the S block cations, which are those first 2 columns of the periodic table, it's pretty simple as well. We just remove the outermost S electrons to get to the nearest noble gas. So we basically remove electrons in the opposite order that they went in. So the last electrons that we put in are the first electrons that come out when we make cations. Okay, so we talked about sodium earlier today, which has a 1s2, 2s2, 2p6, 3s1 configuration. When you remove electrons to form cations, you always remove them from the outermost subshell, which in this case is the 3s1. So to form a +1 sodium cation by losing 1 electron, we just have to lose that 1 electron from 3s, and that leaves us with 1s2, 2s2, 2p6, which again is the neon configuration. So for cations, you just take out the last electrons that you put in until you get back again to the noble gas configuration. So that's how the electron configurations of anions and cations work. You start with the neutral atom, and you either just add electrons to the last subshell or subtract them from the last one you put in. All right, and the last thing we'll talk about today, we'll probably skip the last slide because we're almost out of time, is just how we can compare the sizes of cations and anions to their neutral atom. And it's pretty simple to remember in most cases because cations are always smaller than their parent neutral atom. Because we're removing the outermost electrons, which are furthest away, and so the rest of the electrons that are left are on average closer to the nucleus. So they're smaller than the parent atom because we're removing the outer electrons. And in some cases, we can have different cations that have different positive charges. For some elements, especially transition metals or some of the p-block metals, we can do this. And the higher the positive charge, the smaller it will be. So basically, as you remove more and more electrons, it gets smaller and smaller. So for example, lead can form both +2 and +4 cations. Pb is the symbol. So lead is going to be, it's going to get smaller as it forms a +2, and it's going to get even smaller as it forms a +4. Okay, so the more electrons you remove, the smaller and smaller it gets for that given atom. And then the opposite is true for anions. They're larger than the parent atom. And the reason for this is because now we're adding electrons to the outer subshell. And even though they're in the same subshell as the valence electrons that are already there, we now have more electron-electron repulsions. All right, we saw in the case of oxygen, to form O2-, we added 2 electrons to the 2p subshell. We're forcing 2 additional electrons in. That means those electrons are all smashed closer together. They repel each other strongly, and then they have to, basically the radius expands to minimize those new repulsions. So the more electrons you have in a subshell, the greater the electron-electron repulsion, and that tends to cause them to spread out a little bit and make the atom bigger. Yes? Yes, so that relates to ionization energy we talked about earlier. So the smaller atoms, it's harder to remove the electrons, although once you do, the radius still shrinks. That's always going to be true, but that would be the case for ionization energy. And then the last thing we'll talk about are what are called isoelectronic atoms and ions. These are atoms or ions that have the same number of electrons. And so the radius of these, the positive cations are going to be smallest, the neutral atoms in the middle, and the anions are going to be the largest. So again, if they all have the same number of electrons, but different numbers of protons in the nucleus, the ones that have a positive charge means they have more protons, which are pulling the electrons closer. The ones that are negatively charged have fewer protons, which means the electrons are on average further away. So as an example of isoelectronic anions and cations, if we have calcium 2+, potassium 1+, argon, Cl-, and S2-, they all have 18 electrons, all have the same number of electrons as argon, but the ordering of their radius is going to be as shown. The ones that are positively charged are smaller, the ones that are negatively charged are bigger, and again, they're ordered by virtue of how much positive or negative charge they have. Because the calcium 2+ has 20 protons, so it has more protons in the nucleus, so it pulls the electrons closer. Sulfur has 16, so it doesn't pull the electrons as close, and you have a larger one. And all of these, as I said, have the argon configuration. All right, so next time we're going to continue with the beginning of chapter 3, talking about ionic and covalent bonding. So what happens when we bring 2 atoms together to form a bond, and that'll come next time. But now we at least know how to form ions, and we'll talk about how they bond to each other at the beginning of next class. All right, so I'll see you guys next week. I have office hours right after this if you want to come talk about anything we covered today.